So I guess in particular you can get you can get this to work for any coefficient ring. Yeah. Okay, so as I sort of said out loud, the point of doing this is that this should be the first obstruction to there being a manifold homotopic to our CW complex. So I guess the theorem is so if Mn is a connected, closed manifold, then there exists a finite CW complex complex X homotopic to M such that X is a p-space. So I guess the main question you should be asking yourself is, have we actually defined something new? So it could be the case that any Poincare complex is homotopic to a manifold. So that would make this investigation a little redundant, but it's not the case. So I'm not going to show this because it's quite involved. So there it exists. I'll just sort of point you to where you can find it. So there exists. So let's say there exist p spaces, so that are not homotopic to manifolds. So I guess you want an example. So later on we're going to be seeing a way of coming up with an example by using some extra machinery. But if you want just a hands-on example that of a Poincare complex that cannot possibly be a manifold, there's one constructed in wall. So this is Poincare complexes. So this is in 67. So the first thing to observe, so he even uses some quite heavy machinery to show this. So the first thing to observe is you've got, so say you've got the fundamental group of a manifold is ZP, then the universal cover is a p-to-1 cover, and this is going to imply, so okay, let's also put somewhere that this is a 4 manifold. Of course, this works for any 4K manifold. We've got signature of the universal cover is p times the signature of the manifold. So I guess M is closed. So this works because we've got this this local definition of a signature coming from the signature theorem. So this is the integral of the first Pontryagin class. So this is going to work for any kind of index theoretic kind of description of a topological object. You're going to get this multiplicativity through covers. So then Wall produces, so he produces for all P prime a manifold M with fundamental group ZP. So let's call that MP, a 4 manifold, such that the signature of the 4 manifold, let's say the universal cover, does not equal P signature of MP. And like I say, I think you should look this up because this is sort of the final thing in quite a long paper, and he has to build up the whole paper to express this. So it's going to take a while. So then I guess the question should be, when can we put a Poincare duality structure on our CW complex? Okay. Okay, so section 2. So something I didn't really talk about in my talk my last talk when I should have done, Thom spaces and spherical fibrations. Okay, so I'll say recall, even though I didn't actually say this, so you can't be recalling it. So a vector bundle over a manifold. So I guess whatever properties I want the manifold to have, like let's say it's closed. Maybe I don't need that. So classified by this, so it's a K-plane bundle. So let's say, actually I don't use that. Yeah, so we can give it a metric. Can be given a metric. So with respect to this metric, I can define the disk bundle. So this is the vectors, I guess, in the total space, sort of implicitly fibers, in the fibers, I guess. So this is so these are the disks in each fiber, and these are the spheres in each fiber. And these are fiber bundles over M. So this is going to have fiber the K disk, and this is going to be a K-1 sphere. So this is going to give us something called the Thom space of the vector bundle. So this is the quotient of the disk bundle by the sphere bundle. So Carmen defined the Thom space in her talk to be the point compactification of the disk bundle, I believe, or maybe just the point compactification of the vector bundle. So that works as well, and they're the same. So alternatively, and I think both are extremely useful to have in mind. So alternatively, setting infinity to be, so let's say the point infinity, to be the sphere bundle quotient sphere bundle, we can see that the Thom space is the point compactification of the vector bundle itself. The Thom space is the point compactification I guess you fiber-wise point compactify, but you point compactify all the fibers to the same point, this infinity. Is the space that point compactification of each fiber. So this is not very strict, I guess. To the same point. Which is infinity. Okay. So the point of me restating this is because later on I'm going to construct the whole thing again without vector bundles, and I want to draw your attention to all the bits that are going to be the same and all the bits that are going to be different. So again, remarks. Okay. So the disk bundle is the mapping cylinder So I guess the projection map of the sphere bundle. How do you write mapping cylinders? Like a curly D or something? So let's just say cylinder. Cylinder of the projection map to the base. So we had a bit of a think about why this is true. I think it's one of these things that you can just sort of see. So if this is the total space of the bundle, and this is, this can be M, this can be, so I guess this is fiber, and this should be the fiber of
The total space of the sphere bundle.
the fiber of the total space of the sphere bundle. This is anyway. Yeah. So that's the mapping cylinder, and this is sort of a topic to a disk. So I think this is what's going on here. So that's the first thing, and we're going to try and reconstruct mapping cylinders later. So secondly, I guess the Tom space is the mapping cone. Is the mapping cone of the same thing. The same thing. So let's say cone of okay, so that's all I'm going to say about that. Okay, so then there are various Tom isomorphism theorems, which are going to be very important later as well. So the idea of Tom isomorphism is that the cohomology and homology of the Tom space is very close to the cohomology and homology of the base space. So I guess the rough idea for this is that the cell structure of the Tom space is the same as that of the base space, just shifted up by the dimension of the bundle, I think. But then obviously doesn't tell you that you're going to get these isomorphisms, because the cell maps could be completely different, but in fact you do. So theorem, I'm not going to go through the Tom isomorphism theorems very closely, but I'm just going to state a few of them.